A railway electrification system supplies electric power to railway trains and trams without an on-board prime mover or local fuel supply. Electrification has many advantages but requires significant capital expenditure. Selection of an electrification system is based on economics of energy supply, maintenance, and capital costs compared to the revenue obtained for freight and passenger traffic. Different systems are used for urban and intercity areas. Some electric locomotives can switch to different supply voltages to allow flexibility in operation. Characteristics of railway electrification. Electric railways use electric locomotives to haul passengers or freight in separate cars or electric multiple units. Passenger cars with their own motors. Electricity is typically generated in large and relatively efficient generating stations, transmitted to the railway network and distributed to the trains. Some electric railways have their own dedicated generating stations and transmission lines, but most purchase power from an electric utility. The railway usually provides its own distribution lines, switches and transformers. Power is supplied to moving trains with a continuous conductor running along the track that usually takes one of two forms. The first is an overhead line or catenary wire suspended from poles or towers along the track or from structure or tunnel ceilings. Locomotives are multiple units pick up power from the contact wire with pantographs on the roofs that press a conductive strip against it with a spring or air pressure. Examples are described later in this article. The other is a third rail mounted at track level and contacted by a sliding pickup chute. Both overhead wire and third rail systems usually use the running rails as the return conductor, but some systems use a separate fourth rail for this purpose. In comparison to the principal alternative, the diesel engine, electric railways offer substantially better energy efficiency, lower emissions and lower operating costs. Electric locomotives are usually quieter, more powerful, and more responsive and reliable than diesels. They have no local emissions, an important advantage in tunnels and urban areas. Some electric traction systems provide regenerative braking that turns the train's kinetic energy back into electricity and returns it to the supply system to be used by other trains of the general utility grid. While diesel locomotives burn petroleum, electricity is generated from diverse sources, including many that do not produce carbon dioxide, such as nuclear power, and renewable forms including hydroelectric, geothermal, wind and solar. Disadvantages of electric traction include high capital costs that may be uneconomic on lightly trafficked routes, a relative lack of flexibility, since electric trains need electrified tracks or on-board supercapacitors and charging infrastructure at stations, and a vulnerability to power interruptions. Different regions may use different supply voltages and frequencies, complicating through service. The limited clearances available under catenaries may preclude efficient double-stack container service. The lethal voltages on contact wires and third rails are a safety hazard to track workers, passengers and trespassers. Overhead wires are safer than third rails, but they are often considered unsightly. Classification. Electrification systems are classified by three main parameters: voltage, current, direct current, alternating current, frequency. Contact systems: third rail, fourth rail, overhead line. Standardized voltages. 6 of the most commonly used voltages have been selected for European and international standardization. These are independent of the contact system used, so that, for example, 750 volts DC may be used with either third rail or overhead lines. There are many other voltage systems used for railway electrification systems around the world, and the list of current systems for electric rail traction covers both standard voltage and non-standard voltage systems. The permissible range of voltage voltages allowed for the standardized voltages is as stated in standards BSN 50163 and IEC 60850. These take into account the number of trains drawing current and the distance from the substation. Direct current railways must operate at variable speeds. Until the mid-1980s this was only practical with the brush-type 600 motor, although such DC can be supplied from an AC catenary via onboard electric power conversion. Since such conversion was not well developed in the late 19th century and early 20th century, most early electrified railways used DC, and many still do, particularly rapid transit and trams. Speed was controlled by connecting the traction motors in various series parallel combinations, by varying the traction motors' fields, and by inserting and removing starting resistances to limit motor current. Motors have very little room for electrical insulation, so they generally have low voltage ratings. Because transformers cannot step down DC voltages, trains were supplied with a relatively low DC voltage that the motors can use directly. The most common DC voltages are listed in the previous section. Third rail systems almost always use voltages below 1 kV for safety reasons, while overhead wires usually use higher voltages for efficiency. Since utilities supply high voltage AC/DC, railways use converter stations to produce relatively low voltage DC. Originally they used rotary converters, a few of which are even still in operation, but most were supplanted first by mercury arc rectifiers and then by semiconductor rectifiers. Because electrical power is equal to voltage times current, the relatively low voltages in existing DC systems imply relatively high currents. If the DC power in the contact wire is to be supplied directly to the DC traction motors, minimizing resistive losses requires thick, short supply cables, wires and closely spaced converter stations. The distance between feeder stations on a 750 volts third rail system is about 2.5 kilometers. The distance between feeder stations at 3 kV is about 7.5 kilometers. Because of these problems, modern high-speed rail projects have generally used high-voltage AC once the technology became available. Some DC routes have been converted to AC. There has, however, been interest among railroad operators in returning to DC use at higher voltages than previously used. At the same voltage, DC often has less loss than AC, and for this reason high-voltage direct current is already used on some bulk power transmission lines. DC avoids the electromagnetic radiation inherent with AC, and on a railway this also reduces interference with signaling and communications and mitigates hypothetical EMF risks. DC also avoids the power factor problems of AC. Of particular interest to railroading is that DC can supply constant power with a single ungrounded wire. Constant power with AC requires three-phase transmission with at least two ungrounded wires. Another important consideration is that mains frequency three-phase AC must be carefully planned to avoid unbalanced phase loads. Parts of the system are supplied from different phases on the assumption that the total loads of the three phases will even out at the phase breakpoints between regions supplied from different phases. Long insulated supply breaks are required to avoid them being shorted by rolling stock using more than one pantograph at a time. A few railroads have tried three-phase, but its substantial complexity has made single-phase standard practice despite the interruption in power flow that occurs twice every cycle. An experimental 6 kV DC railway was built in the Soviet Union. The increasing availability of high-voltage semiconductors may allow the use of higher and more efficient DC voltages that heretofore have only been practical with AC. Some DC locomotives used motor generator sets as step-down transformers to produce more convenient voltages for auxiliary loads such as lighting, fans and compressors, but they are inefficient, noisy and unreliable. Solid-state converters have replaced them. State-of-the-art locomotives have even replaced the traditional universal-type traction motor with a three-phase AC induction motor driven by a special-purpose AC inverter, a variable-frequency drive. Overhead systems 1500 volts DC is used in the Netherlands, Japan, Republic of Indonesia, Hong Kong, Republic of Ireland, Australia, India, France, New Zealand and the United States. In Slovakia, there are two narrow-gauge lines in the High Tatras. In Portugal, it is used in the Cascais line, and in Denmark on the suburban S train system. In the United Kingdom, 1500 volts DC was used in 1954 for the Woodhead Transpennine route. The system used regenerative braking, allowing for transfer of energy between climbing and descending trains on the steep approaches to the tunnel. The system was also used for suburban electrification in East London and Manchester, now converted to 25 kV AC. It is now only used for the Tyne and Wear metro. 3 kV DC is used in Belgium, Italy, Spain, Poland, the Northern Czech Republic, Slovakia, Slovenia, South Africa, Chile, and former Soviet Union countries. It was formerly used by the Milwaukee Road from Harlowton, Montana to Seattle, Tacoma, across the Continental Divide and including extensive branch and loop lines in Montana, and by the Delaware, Lackawanna and Amp Western Railroad in the United States, and the Kolkata Suburban Railway in India, before it was converted to 25 kV 50 Hz AC. DC voltages between 600 volts and 800 volts are used by most tramways, trolleybus networks and underground systems. Third rail. Most electrification systems use overhead wires, but third rail is an option up to about 1200 V. Third rail systems exclusively use DC distribution. The use of AC is not feasible because the dimensions of a third rail are physically very large compared with the skin depth that the alternating current penetrates to in a steel rail. This effect makes the resistance per unit length unacceptably high compared with the use of DC. Third rail is more compact than overhead wires and can be used in smaller diameter tunnels, an important factor for subway systems. Third rail systems can be designed to use top contact, side contact, or bottom contact. Top contact is less safe, as the live rail is exposed to people treading on the rail unless an insulating hood is provided. Side and bottom contact. Third rail can easily have safety shields incorporated, carried by the rail itself. Uncovered top contact. Third rails are vulnerable to disruption caused by ice, snow and fallen leaves. DC systems are limited to relatively low voltages, and this can limit the size and speed of trains and cannot use low-level platform, and also limit the amount of air conditioning that the trains can provide. This may be a factor favoring overhead wires and high-voltage AC, even for urban usage. In practice, the top speed of trains on third rail systems is limited to 100 miles per hour because above that speed reliable contact between the shoe and the rail cannot be maintained. Some street trams used conduit third rail current collection. The third rail was below street level. The tram picked up the current through plow access through a narrow slot in the road. In the United States, much of the former streetcar system in Washington, D.C., was operated in this manner to avoid the unsightly wires and poles associated with electric traction. The same was true with Manhattan's former streetcar system. The evidence of this mode of running can still be seen on the track down the slope on the northern access to the abandoned Kingsway tramway subway in central London, United Kingdom, where the slot between the running rails is clearly visible, and on P&Q streets west of Wisconsin Avenue in the Georgetown neighborhood of Washington, D.C., where the abandoned tracks have not been paved over. The slot can easily be confused with the similar-looking slot for cable trams cars. The disadvantage of conduit collection included much higher initial installation costs, higher maintenance costs, and problems with leaves and snow getting in the slot. For this reason, in Washington, D.C., cars on some lines converted to overhead wire on leaving the city center. A worker in a plow pit disconnecting the plow while another raised the trolley pole to the overhead wire. In New York City, for the same reasons of cost and operating efficiency outside of Manhattan, overhead wire was used. A similar system of changeover from conduit to overhead wire was also used on the London tramways. Notably on the southern side, a typical changeover point was at Norwood, where the conduit snaked sideways from between the running rails, to provide a park for detached chute plows. A new approach to avoiding overhead wires is taken by the second-generation tram streetcar system in Bordeaux, France with its APS. This involves a third rail which is flush with the surface like the tops of the running rails. The circuit is divided into segments, with each segment energized in turn by sensors from the car as it passes over it, the remainder of the third rail remaining dead, since each energized segment is completely covered by the lengthy articulated cars, and goes dead before being uncovered by the passage of the vehicle. There is no danger to pedestrians. This system has also been adopted in some sections of the new tram systems in Reims, France and Angers, France. Proposals are in place for a number of other new services including Dubai, UAE, Barcelona, Spain, Florence, Italy, Marseille, France, Gold Coast, Australia, Washington, D.C., USA, Brasilia, Brazilian tours, France. Fourth rail. The London Underground in England is one of the few networks that uses a four-rail system. The additional rail carries the electrical return that, on third rail and overhead networks, is provided by the running rails. On the London Underground, a top contact third rail is beside the track, energized at 7 quintillion 2 quadrillion 420 trillion spade suit plus 420 VDC. And a top contact fourth rail is located centrally between the running rails at 2 quintillion 997 quadrillion 790 trillion spade suit minus 210 volts DC, which combine to provide a traction voltage of 7 quintillion 2 quadrillion 630 trillion spade suit 630 volts DC. The same system was used for Milan's earliest underground line, Milan Metro's Line 1, whose more recent lines use an overhead catenary or a third rail. The key advantage of the four-rail system is that neither running rail carries any current. This scheme was introduced because of the problems of return currents, intended to be carried by the Earth's running rail, flowing through the iron tunnel linings instead. This can cause electrolytic damage and even knocking if the tunnel segments are not electrically bonded together. The problem was exacerbated because the return current also had a tendency to flow through nearby iron pipes, forming the water and gas mains. Some of these, particularly Victorian mains that predated London's underground railways, were not constructed to carry currents and had no adequate electrical bonding between pipe segments. The 4-rail system solves the problem. Although the supply has an artificially created earth point, this connection is derived by using resistors, which ensures that stray earth currents are kept to manageable levels. Power-only rails can be mounted on strongly insulating ceramic chairs to minimize current leak, but this is not possible for running rails, which have to be seated on stronger metal chairs to carry the weight of trains. However, elastomeric rubber pads placed between the rails and chairs can now solve part of the problem by insulating the running rails from the current return should there be a leakage through the running rails. On tracks that London Underground share with National Rail third rail stock, the centre rail is connected to the running rails, allowing both types of train to operate at a compromised voltage of 660 V. Underground trains pass from one section to the other at speed. Line-side electrical connections and resistance separate the two types of supply. These routes were originally solely electrified on the 4-rail system by the LNWR before National Rail trains were rewired to the standard 3-rail system to simplify rolling stock use. 4th rail trains occasionally operate on the national 3rd rail system. To do so, the center rail shoes are bonded to the wheels. This bonding must be removed before operating again on 4th rail tracks, to avoid creating a short circuit. A few lines of the Paris Metro in France operate on a 4-rail power scheme because they run on rubber tires which run on a pair of narrow roadways, made of steel and, in some places, concrete. Since the tires do not conduct the return current, the two guide rails provided outside the running roadways double up as conductor rails. So at least electrically it is a 4-rail scheme. One of the guide rails is bonded to the return conventional running rails situated inside the roadway, so a single polarity supply is required. The trains are designed to operate from either polarity of supply, because some lines use reversing loops at one end, causing the train to be reversed during every complete journey. The loop was originally provided to save the original steam locomotives having to run around the rest of the train, saving much time. Today, the driver does not have to change ends at termini provided with such a loop. But the time saving is not so significant, as it takes almost as long to drive round the loop as it does to change ends. Many of the original loops have been lost as lines were extended.